Previously, we had talked about properties of expectation and variance. So we extended our ideas to multiple random variables. So if x1 through to xn are some random variables, and it doesn't matter whether they're continuous or discrete, we came up with the property that the expectation of a weighted sum of random variables is the weighted sum of the expectation. So it's just a linear function. Now, we also introduced this concept of the variables being independent, and that led us to the idea of covariance. So last time we spoke about covariance. Now, if our random variables are independent, it will turn out that the covariance between any pairs of those variables is 0. And then we get another useful simple property that the variance of some linear combination plus a constant is simply the linear combination of a weighted average of those variables with the weights all squared. So these two properties are going to get extensive use throughout the remainder of the course. So today, we're going to use these properties to investigate special combinations of random variables. Now, the sheet that's attached to this PDF file has an example, and if we have two random variables x1 and x2, and each one of them has the same expected value of 10, and if each one of them has the same variance of 1, we're going to investigate different linear combinations. And we want to see how each of the variance and the expectation are affected. So if we define a new random variable y simply to be twice the value of x1, then using the properties that we just discussed above, it's pretty straightforward to understand how each of these things will get affected. So for instance, the expected value of x1 will simply be doubled here, whereas the variance of y will end up being the variance of twice x1. And this is where you see the variance property kicking in. Now, the weight of any combination will end up being squared. So if we have a combination with a weight that's greater than 1, we'll find that it really gets pronounced in terms of the variance. So having a combination greater than 1 increases the variability dramatically. Now, if we were to add the two random variables rather than doubling one of them, you should be straightforward for you to see that we are simply applying the expectation property we discussed last time, that the expectation of a sum is the sum of expectations. And so this will just end up giving us a 20, which is the same as we had it in the problem above. The variance property, so the variance of y, is slightly different. And it will turn out that we are talking about the variance of one bunch of x1 plus another bunch of x2. And it's important to understand it in that sense because the variance cares very much about the weighting that gets used. So we'll end up getting 1 plus 1 is 2. So in comparison to the combination above where you simply double, the variance is less by adding. So if we add random variables rather than scaling them bigger than 1, we get reduced variability in comparison. Now, we have to talk about the case where you might say, well, if we want to reduce variability, would it matter if we subtracted the variables? From the point of view of the expectation, the expected value should behave very much like you think. So the expected value should then be the difference in these two, and because they have the same expectation, the difference should be 0, and the expected value should be 0. So that's exactly like we expect. But the idea that the variance will change is somewhat interesting. So here we are taking one bunch of x1 and taking away one bunch of x2. But according to the variance property, this is going to have no effect on the overall variance in comparison because those weights will get squared. And so regardless of whether we add or subtract, we will end up getting the same variance that we got above. So what we're doing in these examples is just going in and investigating, right? Trying to understand how different types of combinations affect variance. The last one that we're going to talk about is going to be important for us. So if we take the simple average of the two, this is effectively like saying take 1/2 of x1 and 1/2 of x2. The expected value will behave very straightforwardly. We'll have 1/2 of x1, 1/2 of x2. We can distribute and use essentially the linearity of the expectation. And we end up with kind of a nice result here. We end up with 1/2 of 10 plus another 1/2 of 10. So we end up actually getting the same expected value as x1 and x2. So that's kind of interesting. Now another advantage here, so that you could imagine that being advantageous, right? That your individual random variables end up having the same expectation as the average does. But now if we talk about the variance, I teased this a little bit earlier. In the first example, we talked about using a linear combination with a weighting that was greater than 1. But from the variance properties, you can see that if we use a variance that is now weighted with weights that are less than 1 in size, what ends up happening? So the squaring property really kicks in here. So we'll get 1/4 of the variance of 1 plus 1/4 of the variance of 2. So we end up getting 1/2. And this is the lowest out of all of the ones that we've considered. So it turns out that averaging random variables acts to reduce variability. So in some way, the process of averaging things mathematically reduces the variance, but otherwise, it preserves the expected value. And it's going to turn out that we will take advantage of that. So if we have random variables x1 through to xn, and we assume that they are independent, we are going to talk about averaging. So we're going to define this notation. We'll talk about capital X with the bar. This will be defined to be the simple arithmetic average of all of those random variables. But the right way for us to think about it is as a linear combination weighted by 1/n. So if the random variables are defined this way, if we were to take the expected value, it's going to turn out, as before, to be the expectation of this linear combination. Now, using the property that we talked about above, we can get down to this spot. If for some reason all of the random variables you've got have different expected values, then this is as far as we can go in general. But if we assume that all of the random variables have the same expected value and all of the random variables have the same sigma squared, the same variance, then we can proceed further. Then this will be 1/n times mu all the way down to 1/n times mu. So we'll get n mu over n, and in general, we'll get mu. The expected value of the average is the same as each individual random variable. So as we saw in the example, averaging preserves expected values. The variance of the average in general works very similarly. Because we've said that all of these random variables are independent, we are allowed to use the variance property and split this up and weight accordingly. So we need to square all of those weights. And because we've also made the assumption that we are assuming that each random variable has the same variance, we end up getting this. We end up getting n bunches of sigma squared, and each one of them has the same denominator. So what ends up happening is that the variance gets reduced. It gets reduced by a factor of 1 over n. And that's really important. A reduced variability is a wonderful property in real life. So eventually we're looking ahead, and we are going to be using ideas of averaging to collect data from real life. We would like our data to be reliable as we could possibly have it. And variance is this property where that reliability, that variance goes away, that variability. So we love the fact that an average will reduce this variance. So based on simple properties of expectation and variance, we are able to see that the average is a variability reducing combination of random variables, and we're going to make use of it through